do that, right? I mean, I know there are different styles of learning. I try to accommodate different styles of learning, but I never thought, you know what, maybe I should just teach like everybody else because that's what's going on. And COVID hit, and I kind of like, maybe I'm being unrealistic, you know? Maybe the pattern that I'm using to say, oh, well, this is how university professors do stuff, right? We're not supposed to be able to communicate with, I'm not a university professor, so what am I doing? But what the thing is it's a different style of learning, and a lot of responsibility at a high level is on you, not on me. I already know this stuff. I'm trying to expose you to stuff that's well beyond what you have to know for the class. That's always been my way of doing things, which is, if I've got a smart kid in here, and you're all smart kids, but I want you to be challenged, right? And the people who aren't challenged, there's a certain level of material, and they should just ignore everything above that, right? You come in here and you do this base level, you're gonna pass this class. I'm gonna offer it up here as if you're gonna be a graduate student and come work in my lab, and we're gonna do projects together because I spot you as a special talent. That's the way colleges work. I mean, the bigger, like, so if you're leaving here and going to a real college, right? And not just a community college, not that there's anything wrong with this level. There's nothing wrong with this level. This is a higher level than average, right? I'm just saying, if you want to like soar the sights and get to use the $1 billion equipment, I'm gonna be linear. But see, I was never like that, and now I'm thinking, wow, maybe I'm doing a disservice by not giving you spoon-fed information. But I just, and now that I've said it out loud, no, I'm not gonna do it. Can't. I gotta stay true to it. So, the thing is, it's on you. If I'll go back and do anything at any level, I don't care, right? There's no, where you are is where you are. So to get the information you need to pass this class, it's on you. I will facilitate that in any way I can. I will recommend videos. I will walk through problems. But it has to be you saying, I don't know how to do this problem. It has to be you saying, I don't know, I don't understand what you just said. And it has to be right when it happens. That switch, you have to throw that switch and say, it's my education, I want to know, I don't care what anyone else thinks, I want to pass this class. And not just for my class, but for all classes that you're going to be taking, right? It's on you. You want to get somewhere, you take charge of the bus. You drive, anyway. I think I'm done. Apparently I'm not changing at all. Yeah. So you get what you get. And apparently it's a ton of passion. Okay. So I posted today's notes. Right, hopefully you found those. All right, and let's talk about, I'm just gonna go forward for now, since there aren't any questions. Okay, I've got some stuff, right? What can we, so all science is an observation, and all we're trying to do in chemistry is figure out what's going on with our physical world, right? Here we have what? What can you tell me about this?
White powder.
Good. White powder, does it appear like, how would you describe its relationship as I move it around? Is it kind of
Dry. No.
yeah, it's not lumpy, right? I don't know, I want to say fluffy. I want to say it's kind of a fluffy white powder. Not a hard crystalline powder, right? So I'm going to take some of this hard powder and I'm going to put it in a test tube. Oh, well, maybe I'm not. I should have brought a device to get it in there. I was going to use a beaker, so I guess all right, well.
Piece of paper.
Can you just put the tube in the cup and scoop it
Oh,
in there?
look at that. There's some technique. I like that. Thank you, Maria. All right, now I have this white powder.
Well,
Oh, we don't wanna
sugar.
know.
See, this is how chemists die, right there.
Well, we now know it's edible. So it's-
Apparently it's not poisonous. I just wanted to die in front of everybody. No, I do that every day, so it's not
Send a
new.
statement about the message.
Right, so the next thing I'm gonna do is I'm just gonna put some water in here. So the first thing that I did that wasn't scientific was what? I didn't measure how much powder I put in there. But the next thing I did is scientific, because what am I doing by putting water in here?
Or facilitating a reaction.
You're
We don't know if it's a reaction.
Are you gonna dissolve it?
Yeah, there you go, right? What I'm doing is I'm seeing, instead of saying dissolve, we say if it's soluble. We're checking the solubility in water, right? We also call that aqueous. Oh, I'm sorry, I'm moving around a lot, but I do that. Okay, so aqueous. So now it's an aqueous solution. And whoa, we can tell it dissolves, huh? In water. Whoa. So that's something we learned already. We have a white powder and it's soluble in water, and apparently in water it releases gas. Okay. All right. So that's powder one. All right. Now we have this other little packet. This one's going to go better because it's shaped to deliver. All right. And I'm going to put a little bit less in there so that it get a little bit more solubility. What color is this powder?
It's not quite white, but it's.
Yeah, it's not quite white, and it's not quite fluffy either, right? It's a more hard crystalline white powder. But let's see. Is it soluble in water? And again, I didn't measure it.
Is it expanding?
But boy, there's something happening, right? We'd say, that's not just what happens when you dissolve something. And then look, there was also a color change. Okay. Well, that's two. Then here we have another white powder. And this one also is going to make a mess. Thank God I don't have to do the janitorial. All right. But I will, because you don't leave the place dirtier than you found it. And my mask fell. So this is very similar, right? It's also doing the same thing. It's dissolved. So these two are very similar, right? And over time, this one stopped doing whatever it was doing, right? And now it's got a yellow color. This one's got a yellow color. It's probably going to end up being the same thing. We're very close. And then here I have another powder, and this time I'm going to use Maria's technique for filling the test tube. Right? There's all kinds of ways to earn points in this class.
You can make fun
Yeah.
It's just a protein powder.
of. Yes.
Whoa! Somebody recognizes certain things. So this is a chocolate powder,
Oh.
and old guys, young guys need it, young people need it, but old guys need it a lot because it's hard to get enough protein to keep any muscle mass when you get over a certain age because of your physiology. This chocolate's my favorite. But anyway,
What brand?
no plugs.
No sponsors.
Nice quick.
All right. So this one also soluble. All these are now what? Aqueous solutions.
Yes.
We didn't do any measuring, but normally we want to, right? We want to measure how much we put in, right, compared to how much liquid we put in. So that's what today's lecture is going to be on, partially. Okay, here's one more. Oh, this one. Yeah. Now look at this white powder. Right? Completely different than the other white powder. Right? Bigger crystals. I think it's Himalayan sea salt, right? But anyway, is it soluble in water? And the answer is
Yes.
Well, somewhat soluble, right? Guess I put way too much salt in there. So of all the solutions, right, this one is not what we call homogeneous. As a matter of fact, we have a name for what happens when everything doesn't dissolve, and that is saturated. This is a saturated solution so far. Yeah, it just keeps falling out, right? Yeah, just keeps falling out. So there's still plenty on the bottom. All right. So today we're going to talk about how we measure the comparative amounts of solutions. But the part we're going to do in lab today, which is also similar, has to do with using this device. All right, and it's a very straightforward device to use. It's a conductivity meter, and what it does is it measures the opposite of resistance. Okay, and I put this on the website, but Canvas. So resistance is measured in ohms. Most of us have heard of ohms. A lot of us have heard of, using it as a mantra, but like ohm, right? But it measures resistance. Like you hear a certain ohm circuit, whatever. The reverse of that is a mode, and that's conductivity, which is chasing electrons around, right? It's just a movement of electrons. Measures resistance, which is the resistance to moving electrons around. So this is 1 over resistance. I can't even spell resistance, right? This is conductivity. So it's 1 over, which means the more resistance there is, right? The bigger that resistance, the less conductivity, right? Because it's going to be, so if you have 1 over 1 ohm, it's going to be 1, but if you have 1 over 1,000, it's going to be 0.0, right? 0.001, right? Tenths, hundreds, thousands. Okay, right? So what we're looking for in these solutions is conductivity. And what happens with conductivity is you need separation, right? You need charges. If there are no charges, there's no conductivity. So let's just put it in this salt bath. And right now the reading is 0, and we're always going to push this lower button here. Yeah?
Is your water tap water or deionized water?
The water's deionized. Okay, so this scale maxes out at 10,000 or 100,000 modes. And this is a 10-time probe. But when we put it in here, I get 10,000. When I take it out, in between uses, I'm always going to clean the probe and wait for the probe to settle down. Well, use a little more water in there. Probably could have thought ahead a little bit. But you always rinse the probe with deionized water. Okay. And now it's as it cleanses out, it drops down, and now it's about, let's tap that water out of there. And we're getting a reading of like 500, which is fine. And then let's put it in this other solution, and what does it do? Okay, it's not as conductive, so it's 27,905. So it doesn't max out the scale, which means there's conductivity in there, right? There are ions in there, because that's what makes for conductivity, charged particles, which we know are called ions. right? And it's about 28,000 on the scale, which means there's some in there, but it's not completely ions, right? There's some ions, there's enough to do some conductivity, but it's not the ideal. It won't just let charge go through the solution willy-nilly. And then you, in between trials, this is what we're gonna be doing today. You clean it up, and look, see how the probe kind of gets some of the solution in there. So the next time I use it, now it's back down to 300 or so, which is perfect. I'm gonna look at this vitamin C powder, right? And let me put more water in here so the probe will be covered. And it turns out, no, it's maybe 8,600. So there might be a little bit in there, like a lot more than when we clean the probe with deionized water. Deionized water should be, very low reading because most of the ions are out of solution. This is about 6,200. So we went to max out the scale where everything in the solution is ion, to some of its ions, to a little bit is ionic. And then when you go to the water, you can't keep water completely ion free, even deionized water, because it's gonna pick up ions from the air and self-ionize. So we already did one of these, so we don't have to do that one. Let's look at our chocolate powder. No, not really, 2,300. So you're not getting a lot of ions out of this, but you don't expect a lot of ions in a protein. Why? Because when you're dissolving proteins, you're dissolving bonds between protein molecules. When you're dissolving salt and sodium bicarbonate, you are dissolving ions in solution, right? So if you dissolve a molecule, you're just breaking a bond between molecules. When you dissolve a salt, you're breaking ionic bonds, and that's gonna leave ions in solution. But molecules themselves, remember, molecules are charge balanced, so when you split two molecules that are held together, you're not gonna get any charge, and that's why the protein powder is even lower. There's a little bit of ions from whatever substances they're using, but not the protein. So let me clean this probe off again, and this time do it a little bit trickier. So, one of the things we know, one of the things I know about these packets, right, is this packet contains 1,000 grams no. 1,000 milligrams of vitamin C. Now, we did part of one of our lectures had vitamin C as one of the components, right? Vitamin C is a molecule. So if I put vitamin C in water, do I expect it to be conductive?
No.
Right. I don't, because it's not an ion. It's a molecule. And when you separate molecules with water, you do not create ions. Because molecules, unlike, why are molecules not like ions?
The charge?
Equally charged.
They're not charged. But what two things bond to make no charge? What type of elements bond to make no charge? I'll wait.
Like equal charges?
Metal with the non-metal.
Oh.
That would be what makes ions.
That's it.
That would be what makes ions.
I'd say
Adrian, I didn't say it.
I don't take the credit for it. I didn't say that.
Throwing somebody under the bus.
No.
Right? No, so metal, non-metal, right, makes ions. That's how we know we have an ionic charge. But what makes the opposite? What do we do? How do we make the thought with it?
2 non-metals.
Here you go. 2 nonmetals, or 3 or 4, or however many nonmetals, right? They share electrons. So covalent bonding means molecule. Molecule means no charge. No charge means no conductivity. So substances, generally substances that are not made of a metal and a nonmetal, are not conductive. Metals themselves are conductive. Why? What do metals tend to do?
Grab electrons.
No, nonmetals tend to grab electrons.
Give up.
Give up electrons. So electrons can flow off a metal surface, right? You have electrons on the metal surface. They're away from the center of the atom. They can be ripped off.
Leo girl.
Exactly. Leo goes Gur, right? Leo Gur. That's what I've called Leo Gur. The ogre. Okay. It's French. It's not really. Okay. So we have 1,000 milligrams of this vitamin C that was the molecule that's covalently bound. We dissolve it in water. But what we want to know is how much water, right? When we have a solution, we don't go, well, yeah, I mean, okay, there's 1,000 milligrams, fine. We want to know there's 1,000 milligrams and how much, right? But what do we do in chemistry? We don't say 1,000 milligrams, we say molar mass. Oops. We say 1,000 milligrams of vitamin C is how many moles of vitamin C, right?
Mm-hmm.
So we always convert to moles. That's the first thing. You see any gram amount in chemistry, you're gonna go, he's gonna wanna know moles. You're gonna wanna know moles to deal with that, because the only way we can compare it to other things is with moles, and that's what we like to do to describe our physical universe, is compare things that we know with other things that we know. So here we are, 1,000 milligrams of vitamin C, 1 mole of vitamin C, and then we're gonna wanna know a volume, right, of solvent. So one of the ways we measure things is what we call moles per liter, and that's going to lead us into our molarity. And we're gonna start our lecture right there. Okay. So the important part is, the reason we're looking at this stuff is because we're going to want to know how many moles we can deliver with a certain amount of solution. And what we're doing in lab is you're going to be taking this meter and testing different solutions for their conductivity. And now we know that the ones that are superconductive are ions, the ones that are slightly conductive are molecules being dissolved in water. And they're all in aqueous form. There are also probes for conductivity for solids, but we don't have one of those. And we're not going to use them. Any questions on what I've said so far? All right, so somebody is not using the traditional method. So there we go. Molarity. How do we handle reactions in solutions? Most chemical reactions require solvents to dissolve the reactants and products to form solutions. Why? Because normally you can't mix 2 solids together and have them react. Not always the case, but most of the time that's true. A solution is a homogeneous mixture of a compound. The solute, that's the part that dissolves, the substance being dissolved, and a solvent, the substance doing the dissolving. So if we were looking at vocabulary for the next test, molarity would be good, solvents would be good to know, solutions would be good to know, homogeneous, solute, and then the solvent, what does the dissolvent, right? So we usually consider in all these, all the, yeah, go ahead, Ethan.
Is the solvent of choice deionized water?
Can be. It can be anything. Anything that, what we usually say is the majority component is the solvent. And that can be, depending on the solute, right? If you have an ionic solute, then water is always a good choice. And then if we have a polar solvent, which would be something that has the molecule has a dipole or a charge associated with it, a lot of times another polar solvent will work. So water's often a common solvent, methylene chloride is a common solvent. If you have something that's non-polar, then you dissolve it in a non-polar solvent, something like chloroform. Great question. But usually we consider the solvent the one that's the majority component. So even in this two solids, you can have a majority component that's the solvent in a solid mixture. Okay, so for example, salt in water, which we did right here, and it's still saturated. Good. 10% ethanol in water, right? And whenever you're in water, you get the AQ designation, right? 50% ethanol in water, which is a solvent. Probably water. Yeah. But it's a top solvent. So this is the way, yeah, it's kind of vague. I got this much of this. That's what I did here, right? I did the vague approach to measurement. Yeah, I put a little bit of this, a little bit of that. Yeah, it's good. It's pasta. Okay. Amount of stuff, amount of solute. Not really for quantification, right? You need numbers. You need to be able to. I can't just go, yeah, I put a little bit of this and a little bit of that, and bing a boom, I got this nice chemical. That won't translate to a guy in another country. So I need to put numbers associated with it so that I can tell you specifically how to make something. So for us chemists, we say moles of solute, right? There it is. What's being dissolved? We need to know the number of moles. And what do? We take the grams and we convert to moles, and now we have moles of solute. And then liters of solution. So we measure it by the liter, moles per liter, right? A given amount per given volume. Liters of solution does not equal liters of solvent. Why would that be?
Because the solution is the entire thing. Solvent is just one component of it.
Mm-hmm.
Correct. Nice answer, Dawn. Right? Liters of solution is the entire solution, including what's dissolved in it. Liters of solvent is just what we're using to dissolve. Okay? Not the same thing. So in this case, we take something and we fill it up to 1 liter after we put the solid in there. That's the solution. If we do a liter of solution, a liter of solvent, and then we add the component, we've got more than that. So we have to be careful. And that's why we often use volumetric flasks to make these mole per liter solutions. So when you see something that says, and the way we write that here is, let's say we had H2SO4, right? And then we said aqueous, and then we said 2.0 M. That means 2 moles H2SO4 in 1 liter of solution. And I don't know how I got this math to be so loose. Anyway, okay. Making a 1 mole of solution, how do you do that? Incorrect, you add 1 liter of solvent to 1 mole of solute. And correct, to 1 mole of solute, the part being dissolved, you add solvent until you get to the total volume of a homogeneous solution of 1 liter. right? And we just talked about that, and I just reiterated it. So examples, what is the concentration of 14.7 grams of sodium cyanide, 49 grams per mole in 150 ml of solution? Alright. So here we go. We're doing it, not just me. Alright. So we know molarity. Get all these nice new pens. This is what I use.
Good shot.
Thank you. You know, a guy's got to be able to do that. It's just a thing. All right. So we have 14.7 grams. 14.7 grams NaCN. All right. And I'm so nice, 14.17.
You can leave the projector up, but not the board down.
Huh? Yeah, whatever. I'm doing it this way. Thank you, though. 14.7 grams, we can talk about that at another time. In 150 mils. What do we call that? Solution. H2O, that's what we have there, H2O. All right, so 14.7 grams of this in 150 mils of H2O. And what do we want to know? We want to know what is the concentration. So we want to know what's the molarity. Big M, moles per liter solution. Okay, so the only volume we have is this, so it's going to go here. We're going to put this gram amount here, but that's not moles. We have to go grams to moles, right? So we take our 14.17 grams of sodium cyanide, right, which we recognize because CN is cyanide, and it's a 1-to-1 ratio with the alkaline metal, which has a 1 charge, and it's 49.01 grams per mole. So 1 mole sodium cyanide is 49 point, what did I say it was? 1?
I didn't catch it.
Are you just getting that 49 from the periodic table of Na?
Right, so C is 12.01, nitrogen is 14.07. And sodium is 23.98. Or close, 22, 23. So I just passed out periodic tables. You should always have your periodic table, especially if you're gonna be solving.
It's 22.99.
Yeah, see, I always try to make it 23 and it's 22.9. And so we add that up together, 10, 7, 0, 1, 4. Oh, did I, yeah, 10. So it's close, I'm a little, yeah, 01, 07, whatever. 5, I can't, the math is just killing me. 4, 9. So very close, depending on what your table is, that's what we got it.
49.02, I think.
Yeah, well, whatever, I had this.
Pretty close, yeah.
So, grams, sodium, cyanide, depending on the table. This one, you would have used 49.07. I'm not gonna ding you if your periodic, if you show this and your number is different than the one I put on the final, on the exam, right? So to me, that is this. It's with it, because why? Because we're talking about this much, right? We're talking about 1/100 of a gram. You sneezed. Anyway, this, so we convert to moles. You with me?
Mm-hmm.
All right. What is that? Do that on your calculator.
.2819.
So I don't like to leave decimals naked, they get
0.2891.
cold and afraid.
91, .2891.
I'm gonna need confirmation.
Yeah. I
No,
put
no,
the
I
last
mean-
two numbers.
2891.
Yeah. That's 19891. That's correct on the board. I'll shut up.
And that's moles, right? Moles, NaCN. Alright? And we have 150 milliliters here, right? But what we're looking for is liters. So we have to do that conversion, right? 150 milliliters times 1 liter is 1,000 milliliters. So when we come in to fill in our moles per liter now we have our two numbers. 0.2891 moles NaCN, sodium cyanide, and we have 0.150 liters of solution, right? So this is the solute per amount of solution. Put that in your calculators, and that's going to give you the big M. And let's see if we can do that one as well. Right.
Do you still have to attach the water to it, or can you just say solution? Like, cause you,
That is the solution. That's what that is.
no, I know, but do you still need to write H2O up there, like on our?
No, because it's the solution. Now this is dissolved in there,
Oh, okay, I got it.
right? So whatever the solvent is becomes immaterial because now we're looking at the entire solution.
I got 1.9273. Repeating.
Mm-hmm.
Same.
Okay. And so that is moles per liter of solution of sodium cyanide. So that's how much sodium cyanide is in there. We would go with two significant figures because we have a 150, right? So 1.9 molar NaCN, all right? And so if you see something like this, now we know what it means, right? There, in every liter of solution, there's 1.9 moles. And we know that 1.9 moles in a solution of 150 milliliters is 14.7 grams. So if we were going to make that solution, right, if we're going to make a 1.9 molar solution of sodium cyanide, and we only needed 150 mils of it, we dissolve 14.7 grams. And we can go the other way to get it as well. All right, and often do. All right, we're going to have another example. How much sodium? Oh, look, I did it. Imagine that. So now we're going to do it twice. No problem. Right? And we got the same numbers. Pretty damn close. But I counted that. This should not be, should only be two significant figures. I counted to 0. I shouldn't.
Do you always just go with the smallest one, or do you
Yes.
use the solution?
How much would you dock us off if we throw like you did right there instead of the 1.9?
I mean, depending on the complexity of the problem, probably just 1. If this is, that'd be like a 10-point problem. You get 9.5. Maybe I might even ignore it depending on how I'm feeling. If I catch it. Like I just caught myself, I'm embarrassed, right? I could fix it by putting a decimal in there, which I should just do right now. As if I'm ever gonna use these slides again. All right, where was it? There. Okay, all fixed. Uh-oh. What problem? What are you talking about? There's no problem here.
There never was a problem.
No, never was.
Right from the start.
Okay, so the second one, we're gonna do the same way, right? I'm gonna actually let my slide do the talking this time, because we went through the process. So how much Na2S at 78.04 grams per mole is needed to prepare 75.0 milliliters of a 0.750 molar solution? All right, so let's not do it with the slide. Let's do it this way. Because I like. So no one has any questions about the material we've already covered? Still feeling like there should be some.
Like previously to today or just?
Yeah, like leading up into Thursday when you take the test.
Yes. How much time do you have?
Hours. Okay, let me, I wanna get through a little bit of this stuff. Just up until the conductivity part. And then I'll be glad to do the rest. Where are we? Oh yeah, we got lots of time. I feel like I've been already talking for 2 hours, but I haven't. Cause I got all excited about that demo.
Leave the light off, it's actually easier to see the red marker without the light. Am I the only one?
So here's something. When you're looking at molarity, big M, right? Moles per liter. So let's write that below. You got to remember this is molarity and not mass. Okay. So for what we just looked at, right, Na2S with a molar mass, right, calculated from our periodic table, 22.98 twice and 32.06, 78.04. Grams per mole. And what is that? Na2S, Na2S. So that's our mole weight, right? And what else do we need? 75 mils ml of 0.750 molar, right? Na2S. All right. So our molarity, right? The M there, big M, is 0.75. And whenever I see the big M, I just do this immediately. Moles per 1 liter, right? Because it's a ratio. Molarity is a ratio, concentration, this per that. So I have that, and then I have 75 mils. Except for, what do I have to be in? Those don't cancel, so this has to be converted to 1 liter is 1,000 mils. And this is gonna give us a number of moles, right? So let's do that. Right, so molarity times volume, moles.
Like 0.5625? No one else?
Mm-hmm.
And then I always, again, like this was the hardest part for me as a student, label your answers. Label your answers, always. Yeah,
I think it was 0.05.
Oh, yeah, it was.
0.0. 0.0.
thank you. Keep me honest. All right, and now what do? We're in moles and we want to know how much we're going to add to that solution, so we have to go to grams. My, what big teeth you have, Grandma. Okay, so 78.04. That's our ratio, right? 78.04 grams Na2S divided by 1 mole Na2S. Now moles cancel.
$4.397.
Yeah? All right, and then we go back and we see we have 3 significant figures. That's 4. Good job, Jim. All right. It's a specific skill set to be able to squeak markers. All right. So what we did here, right, is we said, wow, I want this much of this. This is one of the secrets of the universe, right? We now know that we can make any solution of any molarity using these ideas, right? I can take a gram amount, dissolve it in a volumetric flask, and get an exact molarity of anything. And if I use the stoichiometric ratio of a balanced chemical equation, I can convert that into any product I want to. Now there's some caveats, which is why trailers that make meth explode, but you are available to use these techniques in every single situation that involves chemicals, including biology. Just saying. And your body functions on this principle of molarity to balance its pH. All right, so what else do we need?
Will you turn the light down? So we can see it?
Eventually.
Thank you.
Thank you. And feel free to, boss me around, I like it. All right. So, yeah, look, we got the same answer. That's good. So we took moles per liter times volume and converted back to grams. I mean, it's really a tool. It's a really big tool. Oh, we're gonna do one more, right? I'm not doing this one on the board. How many milliliters of 0.442 molar sodium nitrate, right? So 0.0442 moles per liter, and we're given 43.23 grams of sodium nitrate. So we're gonna convert that to moles too, right? Because we have grams, we're gonna go to moles. So how much can we make? All right. So volume equals moles divided by molarity, right? Which is liter moles, right? We want to get rid of moles, so moles go on the bottom. This is part of the technique. Whenever you see a number that isn't associated with another number, that's the conversion number. Whenever you have a ratio, that's the ratio you're going to use to do that conversion in all problems. The one that's not associated is the one you're going to change. All right. So 43.23 grams, that's what we're starting out with. Sodium nitrate, we have to be able to convert. Using our periodic table, right, the metal comes first, sodium. This one doesn't have the parentheses that it should. Note to self, be consistent. And now you recognize it as a, right? Oh, let's just, yeah. Do this a bunch of times. Oops. Boy, I'll never make it as a computer programmer these days. Okay. Still won't. I got rid of the 3 too.
Oh boy.
That's nice. All right, we can fix the rest later. Or never. Whatever the case may be. But you get the idea, right? That's gonna tell us that it's a polyatomic ion, and then we can look at the worksheet that we have with us so that we can name that compound, sodium nitrate, and then minus charge. So we're gonna have 43.23 grams of sodium nitrate. Our solution, right, is grams. We're gonna go to moles. We're gonna find out how much moles we're starting with. And then we're gonna say 1 liter of 0.442 molar sodium nitrate times milliliters gives us 1,150 milliliters. Very nice. You guys got that?
That one kind of threw me off. How are you, see, like, to me, that sentence in the top isn't really, attaching one of those numbers to the liters, the, liquid or the salt,
Okay,
does that
so
make sense, what I'm saying?
because so the first one, milliliters, right? That's our volume,
Okay.
right? And it's by itself, so we're gonna have to convert milliliters to liters, right? And then the M tells us moles per liter, right? So we know, so let's look at what we have then. Here we go. I guess I'm doing it on.
Sorry.
No, don't be. It's exactly what I want you to do.
I need to see
And I'll
it
use
too.
Dom's idea
I
now.
need to see it too, cause I didn't get it.
I thought you said you had a tear too. I
No,
was like,
no, I
do
was-
I? Is it coming out?
Wow, I'm erasing the screen.
I don't even know what's happening anymore.
That's just words on top of words.
So I'm gonna look at this problem. Oh, I can't reach it.
Oh,
All right, and I'm gonna pull milliliters down, and I'm gonna pull 0. I don't even like to read problems because it gets in the way of solving them. All right. And then 85.0 grams per mole. And 43.23 grams. Sodium nitrate. Is it better with the light on or light off?
Right on. Well, let's see.
off.
1 or 2?
Off, 2.
All right, so we have a bunch of things here. Okay, what's my first relationship to me? My first relationship is I'm in grams. Do I have anything that'll convert? Here we go. Uh, 85.0 grams sodium nitrate. And look at me, not even putting the parentheses on the board. Okay, so now I'm in moles of sodium nitrate. What else do I have that's moles? Oh, I have this. Remember, whenever I see the big M, I do moles per liter, right? So now I'm gonna go, I wanna get rid of moles, so I'm gonna use it upside down. I'm gonna go 0.442 moles per 1 liter. And then, what else do I have? I have milliliters. Well, 1 liter is 1,000 milliliters. Wow.
Done.
And then that works out to 1,150 milliliters.
Multiply the top, divide the bottom.
So I don't even know, right? I just picked milliliters. I just took the information, the numbers that I had. I said, this is grams. How do I convert grams? I look for moles. I mean, there is a logical progression, right? The logical progression is volume equals moles divided by molarity, right? Because molarity equals moles per liter, which is moles per volume. So if you want to look at that, then if you solve for volume, right, volume comes across, and then you have molarity, moles stays here, and you divide by molarity, which is moles per liter. And you end up, right, that equals liters, because these cancel. This is 1 over liters. There we go. 1 over liters. Right? 1 over liters, which brings it up top. Algebra. Helpful, not helpful?
Medium helpful.
Ooh, medium, that's pretty good. That's better than complete strikeout. So we're starting with the gram amount, and we want to know how much of a certain concentration we can make.
Right. Which your first equation that you did made absolute sense, but there's only like 3 things involved, 3 parts involved. This seems like it has an extra part or number to it, I don't know, in my head. Am I the only one that sees that now?
Okay, so the numbers we're already used to, right? The 3 numbers we're used to. How many grams we have, right? We're used to that. We're used to going from grams to moles, right? This is just the molar mass, right?
Can you turn off your monitor here so I can see it clearly?
Sure.
Thank you.
Oh, that 85 is just the, moles from the periodic table, you just gave it to us in the problem?
Yeah, I gave it to you in the problem.
Oh, see, I was seeing it as like there's an extra number in here.
No, I just calculated the molar mass, which is then used right here.
Okay. Then I'm not as confused.
Anyone else?
What else? Good.
Oh, boy.
There's another one.
Yeah, there's more. Wait, there's more. Molarity.
Can we keep working on the board? This is honestly the best way to shove it into our heads, in my opinion.
Hey, well, you know what? It's your education. So I'll shove this stuff into your head any way I can. And if you like a particular way, then let's stick with it. All right, we've got, what is the molarity of sucrose C12H22O11?
Oh my gosh.
Toss it.
You are striking out the pens today.
I do. I like.
Took all mine to
I'm
Santa
using
Barbara.
up. I'm using up all my goodwill, and I already took a good shot. So you got to get into paint.
Don't test it.
What did I say? C12H22O11. C12H22O11. Right? And how much is in Mountain Dew?
Oof.
From fortunately I happen to know that. From the label we see that 8 ounces. And I'm not going to make you do that conversion, but 8 ounces is approximately 240 milliliters.
Oh, thank you.
But that would be a great thing to do. It has 30 grams of sugar in it.
So are you never gonna give it to us in liters? We just have to,
Yeah, that's always going to be in milliliters.
Okay.
Life's always in
I'm just
milliliters.
asking.
Grams of
Senior trend.
C12H22O11. And a little factoid I learned after I had cancer and all my systems went out of whack and I got diabetes as well, is that 4 teaspoons of sugar, how does that work? There's 4 grams of sugar in each teaspoon. So when you get to this level of sugar in a soft drink,
Oy.
you're literally, and there's a great documentary on it. And the guy, instead of eating the food, he just takes spoonfuls of sugar. So this would have 9 spoonfuls of sugar, teaspoonfuls of sugar. So that's like 1, 2, 3, 4, 5, 6, 7, 8, 9 in an 8-ounce can.
Yeah.
Like, we're not supposed to be eating that much sugar, I guarantee you.
So off the subject there, is the zeros the same thing? You know how they have zero now sodas?
Well, they're different. They have 0 sugar,
Yeah.
but what they usually have is either a fake sugar
Yeah.
Like
or a sugar alcohol, because somehow sugar alcohols pretend they're not sugar, but they are. So you're really eating, sugar alcohol is really sugar with an H on it. Like, so the sugar is a carbohydrate chain, and this is a 2 sugars, right? So instead of C6, it's C12. But the only difference between this and a sugar alcohol is one of the oxygens on here, one of the 11 oxygens, has a hydrogen on it. That hydrogen comes off in your body. It's just still sugar. I don't know how they get, because the people working for the FDA are not chemists. They're biologists. Oh, I'm sorry. That's not true. They're chemists. They're just bad.
People.
Yeah, I don't know. I don't know if I disagree with guys that have enough money to make you disappear.
Also,
It would be stupid.
They're
All right.
smart, but.
Yeah, they're living scientists. 30. So we have 30 grams of sucrose. All right, and then we're going to convert that to moles, right? C12H22O11. And believe me, when you're doing organic chemistry, that gets old. I had to write it like 15 times last night. And what do we say that is? 342.3 grams, 1 mole. Well, at least you're only getting 1/10 of a mole of sugar, right?
That's not so bad.
So instead of 6.022 times 10 to the 23rd, you're getting 6.022 times 10 to the 22nd molecules of sugar. Oh, I was so mad. And I used to drink Mountain Dew like a madman when I was in grad school. Yeah, it's lucky I have any teeth. All right. And that comes out to be what? Oh, and then we have to, right? So what are we doing here? We're finding molarity, right? Question mark, big M. Big M, moles per liter, right? So 30 grams sucrose, remember to keep it going, CH22O11, 1 mole, oops, C12H22O11, times what?
No, the,
Divided by, right? 0.240 liters. Right, that's a molarity, moles per liter. Right, can you see that? Right, we're gonna take the number of moles, which is this. And what is that, 0.365.
I think I missed it. Where'd you get the 0.240 liters?
That's the 8-ounce can.
Oh, okay.
So in an 8-ounce can, we have this many moles divided, and it would probably be helpful if we did that step, right? So if somebody wants to do that math right there.
Sure.
Like I said, it's gonna be about a 10.
wait, 0876
.0876.
4242. Sorry.
That's all right. 0.240 liters. that's the 0.365.
Thank you.
So
You're
quite.
saying, sorry, real quick, you're saying 0.24 liters because that's 240 milliliters. You did that step. You just timed it by 1,000. But you don't, as long as we don't, it's okay if we don't show you that?
Yeah, it's okay if you don't show me that.
Okay.
That one I can see, and that one we do enough that it's,
Well, I know there's certain numbers that are supposed to be common knowledge. Is that,
if you have trouble going from this to that, show that. If you show it, you won't lose points even if you do it wrong. If you don't show it and you do it wrong, I'm like, where that? I don't know what the.
got it.
Okay. All right, so let's skip this part for now. And this part for now.
There'd just be one sig fig in that? From the 30? right?
Yeah, because this isn't 30 point, right? You're right.
0.3.
0.4.
So like in the lab, in the, one of the other problems that you did prior to this,
Yeah.
you had a number in front of the molarity symbol.
Right, that would be here.
Oh, so you were given it first, so it was more of a working backwards?
Right.
Got it.
Right, so that's what we just did. We worked through all the permutations of molarity by going, if we have a certain amount of grams in a liter of solution, what's the molarity? If we have a certain molarity, what's the amount of grams? If we have a certain molarity, what's the volume? Right, because those are the three parameters, moles per liter. So we have grams. Remember, grams, we just have grams to convert to moles. We measure everything in moles, so I can say, now I have this solution of 0.4 molar C12H22O11, what can I react it with? And now I have a number of moles, and I don't have to worry about the grams. I can just find something. If it's a 1-to-1, then I know I can use 0.4 moles of something else. If it's a 2-to-1, then I can use 0.8 moles. Let's see, the last. Oh yeah, we have all that. Ugh. I was gonna go over that again. That'll start. Here's the thing we have to know for today in lab. You want me to do it in lab? I can do it in lab. Let's take 5 minutes right now. And so I can calm myself down. Thanks.